All right, so let's take a look at question number 5 and beyond. I think the ones that at the top you guys got, but the thing that I was hoping you would get from this is one of the strategies that's super helpful when you're solving these equations with exponentials and logs is to be able to go back and forth between exponential form and log form. So a lot of times, if you're trying to solve a log, you're trying to solve for something that you're taking the log of, and you really want to get that little question mark out by itself. And the way you can do that is by doing an inverse operation, and the inverse operation of logs is to write it as an exponential. So if we look at this first one, we want to try and get the question mark by itself, but the first thing you want to do is isolate just the log. And so you could add 4 to both sides, and you get log base 3 of the question mark equals 9, and then change it into exponential form. So you would take the base of the log is 3, that stays the base of the exponential. What the log is equal to is always the exponent, and then the question mark goes by itself. So when I'm doing this, I always imagine like the base stays the base, and then I imagine like those other two things kind of being animated and kind of switching places. So the 9 is going to come over here with the base, the question mark is going to go by itself, and then you can evaluate that. In this case, you could use your calculator to figure out what 3 to the power of 9 is. Any questions about that one? All right, so this is an exponential equation because it has the unknown thing. The question mark is in an exponent. And so what you want to do is get the exponential part totally by itself. So you want to get rid of the 5 first. And then you could write that as 2 to the power of 7 minus the question mark equals 8. And then you could rewrite that as a log. So you could say log base 2 of 8 is equal to 7 minus the question mark. Well, what is log base 2 of 8? 2 to the power of what equals 8? 3. So 3 is equal to 7 minus the question mark. So the question mark is going to be equal to 4. This one here, the log is already by itself, so you don't have to do anything else first. And so we can go ahead and start to write that in exponential form. Remember, when there's a natural log, there's really a base of e. We just don't write it. So when you're changing it into exponential form, your base is going to be e. This is going to go into your exponent, and then this part is going to go onto the other side. And then e to the power of 0 is equal to 1. Anything to the power of 0 is equal to 1. And then you could either just kind of think in your head, well, what would make this equal to 1? What would the question mark have to be? It would have to be 9. If you didn't see that, you could also solve it by squaring both sides and then solving the equation from there. Any questions on those? All right, the next set of questions here in question number 6, we're going to use something that's called the one-to-one property. And the one-to-one property basically says, like, if you have an exponential equation and you have the base on one side is the same as the base on the other side, and then they're raised to exponents, it means the exponents have to be equal to each other. So if 4 to the power of some unknown thing is equal to 4 to the power of 11, that unknown thing has to be 11. And so same thing here, if our bases are the same, we know that the question mark minus 1 has to be equal to 20. And so the question mark, oh, sorry, there's a 3 in front here. And so then we can just solve that equation. And the question mark is equal to 7. So essentially, when you have an exponential equation where the bases are the same, you can just really make a new equation just with the exponents. Since this equation is true, the exponents have to be true as well. And this is, you could have, like this one here on 5b, you could have done that the same way, because this 8 here, you could have written that as 2 to the power of 3, and then your bases would have been the same here. And then you could have set the 7 minus question mark equal to the 3. You would have got the same answer. It's just a different way of thinking about it. So a lot of times with these equations, there's more than one way to think about the way that you would solve it. And then the same thing is true for logs. If I have log base 4 of question mark is equal to log base 4 of 10, then my question mark has to be equal to 10. And so it's not like the logs cancel out, but you don't need to include them in your equation anymore, because if the logs of those two things are equal, then those two things have to be equal to each other as well. And so a really good strategy when you're trying to solve logs is to try and get two logs on both sides that have the same base. And in this case, we have this log, and then we have these two logs subtracted from one another. So what you want to do is you want to rewrite it as one log. And so you're going to use one of the log properties that we did before. Since we're subtracting the logs here, we're going to get, this is going to be equivalent to the log base 7 of the question mark divided by 2. And so therefore, those two things, the 20 and the question mark divided by 2, are going to be equal to each other. So you're going to make a separate little equation there. I'm going to multiply both sides by 2, and so the question mark is going to be equal to 40. Questions? All right, let's take a look at this last one. So the last one is going to kind of combine a lot of different things that we've talked about so far. And we have logs on both sides. So the first thing you would want to do is just rewrite it as, sorry, I should have written here a single log. You want to do the same thing here. So you could rewrite the left side as a single log. Since these two logs are subtracted, that's going to be equivalent to the natural log of x plus 6 divided by x. And again, we now have the bases of both sides. These are both natural logs, so those parts are the same. And if that's true, then that part's going to be equal to each other. And so you can make a new equation that's just going to take this part of the equation. So you can say that x plus 6 over x is going to have to be equal to x. And then let's solve that equation. So this is just a proportion, and you can solve it by doing the cross product. So you can do 1 times x plus 6 is x plus 6. X times x is x squared. Go ahead and finish solving that equation if you haven't done that already. Did anyone get an answer for this one, by the way? Okay, let's go ahead and finish solving that. And then we're going to check this on our graphing calculator. So go ahead and get your graphing calculator out. If you don't have one today, come and borrow one up here. And so you need to be able to solve these algebraically by hand. But I want us to take a look at how you can use the graph to help you to check your work. So let's go to the graphing calculator, and what you're going to do is, what's that? Sure. So when we did this algebraically, we got x equals 3 and we got x equals -2. So let's take a look at how this would look graphically. So go to your y equals, clear out anything that's already there. And then go to y1, and we're going to enter in the left-hand side of this equation into y1. So you're going to do natural log of x plus 6, and then minus natural log of x. And then go to y2. We're going to put the right-hand side of the equation into L2. So on the calculator, as soon as you start entering a log expression, it's going to open a set of parentheses. You want to make sure you close it at the end. All right, so once you have that done, go to graph, and it's going to put both of the equations in there. On mine, it does it in different colors. Yours might not be, but that's okay. And does it look like it intersects where x equals 3? Yeah. If it's not as obvious, you can also do something on the calculator where you can find the intersection. You press second and trace, and then scroll down to intersect. And then it's going to ask you first curve, and you just press enter. Second curve. Oops. You press enter. Oh, it's not working. Here we go. First curve. There we go. Okay. Normally you just press enter 3 times, and it's going to give you your intersection. So it's only intersecting when x equals 3, but when we did this algebraically, we also got a solution of x equals -2. So what's going on? Yeah. So why is x equals -2 not a solution? Yes. Hold on a second. I'll help you with it in a minute. Right. So remember when we did the domain of a log function, what is the domain of a log function? X is going to be greater than 0. So if you try and put a negative number into a log, it is not part of the domain. And so if you look graphically, there's nothing on this left side here. And so it's not going to be a solution. So sometimes when you do these algebraically, you get what's called an extraneous solution. And x equals -2 is extraneous. It basically means it's kind of an extra solution that you get from solving it algebraically. However, it doesn't really work when you substitute it back into the equation. So there's occasionally certain equations that have restricted domains like square roots and logs end up with extraneous solutions. So you want to just make sure when you get your solutions, check and make sure that when you put them back into your original equation, you're not getting any negatives that you're trying to take the log of, because that's not going to work. Questions? All right, let's go on to the next page. We're going to kind of summarize some different ways of solving exponential and log equations up at the top, and then we're going to work through some examples together. So let's go ahead and write this down, please. So we're going to list some strategies for solving exponential and log equations. One of the strategies that you're going to use a lot is you're going to apply the log properties that we learned last week. We're going to use a strategy that you've been using for solving equations since you first started solving equations, which is to use inverse operations. Another strategy that you're going to use a lot is to rewrite the equation in an alternate form to isolate the variable. So if it's written as an exponential, you're going to write it as a log. If it's written as a log, you're going to write it as an exponential. And the other one we're going to use is the one-to-one property, which says that if you have a base to the power of x, and that's equal to the base to the power of y, then x and y are equal to each other. Or if you have log base of x is equal to log base b of y, then x equals y. And in order for this to be true, the bases must be the same. So you want to think of this almost like a menu of different choices that you have when you're solving an equation with exponentials and logs. You're going to use one or more of these strategies depending on what the equation is that you are given. So let's work through a few examples. So the first one, we have log base 49 of x is equal to 1/2. This one, we're given a log equation. What we're trying to find is kind of buried inside the log. And so we're going to use this strategy here to rewrite it as an exponential. So our base is 49. We're going to move the 1/2 into the exponent. That's equal to x. And remember, an exponent of 1/2 is just a square root. And the square root of 49 is 7. The next one is an exponential equation. And so you could rewrite it as a log, maybe. But what you want to do first is get that kind of exponential part totally by itself. You just want like a base and an exponent. So let's get rid of the 10. And you would get 6 to the x equals 36. And then at this point, you kind of have two choices. One is to rewrite it as a log. You could write that as log base 6 of 36 equals x. And then just think to yourself, 6 to the power of what is 36? That's going to be x equals 2. Or you could take that 36 and you could rewrite that 36 with a base of 6. And then since you've done that, the bases are the same. And you can use the one-to-one property and you get x equals 2. You get the same answer regardless of which way you do it. You can choose whichever way makes more sense to you. Go ahead and try this next one. So start by getting the e to the x plus 1 by itself. And then rewrite it as a log. Remember, if it's a base of e, you can just write it as ln. And then you would just subtract 1, so you would have ln of 15 minus 1, and you can put that into your calculator. And that's approximately 1.708. Any questions on that one? All right, the next one's asking us to use the one-to-one property. So this one here, we're just going to take, you'll see we have a natural log on both sides. If that's true, then this part has to be equal to each other. And so we can just make our own separate little equation that looks like this: 2x minus 2 equals 11, and then solve that. The next one is asking us to use the one-to-one property. And right now we cannot use the one-to-one property because we don't have the same base on both sides. So what you would want to do is start by rewriting an 8 with a base of 2. So we know that 2 to the power of 3 is equal to 8. And so now that you've done that and you have both bases the same on both sides, you can now set the exponents equal to each other. And so again, you can just make a separate equation: x squared minus 6 is equal to 3. And we can just solve this by taking square roots. Remember, when you solve a square root equation, you're going to end up with two solutions: x equals positive or negative 3. Any questions on that one? All right, let's try number 3. So for this one here, you want to rewrite it as a single log. So we're going to use our log properties. And when you're doing that, remember, you always want to move whatever's in the front into the exponent first. So I'm going to say log base 4 of x squared minus log base 4 of x cubed. And then these are subtracted. So I could rewrite that as log base 4 of x squared divided by x cubed is equal to 1. And I could actually simplify this now. So I could simplify that, and it's just going to equal 1 over x inside there. And so once I've written it as a single log, now I can rewrite it in exponential form because I want to try and get this x out of there. So I'm going to have 4 is my base. This is going to become my exponent, and it's equal to 1 over x. So if 4 is equal to 1 over x, if I just take the reciprocal of both sides, I'm going to get 1/4 is equal to x. Any questions? All right, let's try this next one. It says to use your graphing calculator, but we're going to first do it algebraically. So what you want to do first is get that exponential part kind of by itself and get rid of the 6. So I'm going to divide both sides by 6. I'm going to get e to the power of 1 minus x is equal to 25 over 6. And now I'm going to change that into log form. So if my base is e, it's going to become the natural log of 25 over 6 is equal to 1 minus x. And now to solve that, I'm going to subtract 1 from both sides. And then I have a negative x here, so I'm going to have to divide everything by negative 1. So then go ahead and put that into your calculator. And we're going to get x is approximately 0.427. So let's go ahead and check that on your graphing calculator. So on your graphing calculator this time, put the left hand side of this equation into y1 put the right-hand side into y2. And then see what your equation looks like. So go ahead and clear whatever you have in there. And then into y1, I'm going to put 6. And then e to the power of 1 minus x. On the other side, I'm going to put 25. And then when you go to graph it, you only see the exponential one, you don't see the other one. Why not? Because it's 25 and our window is not showing us 25. So we're going to need to zoom out. So just click on the zoom button and you can just go to zoom out and then just press enter again and it's going to zoom out. And so if you look at that, we cannot really see very clearly what our intersection is, but our calculator can calculate it for us. So we can press second and trace and then go down to where it says intersect. And then it's going to ask you for your first curve, you just press enter. Second curve, you press enter. Guess, you press enter, and it's going to give you your intersection, which is the same as what we just found algebraically. Sure. You're going to go to zoom, go down to out, press enter, and then press enter again. And then if you've zoomed out and you want to go back to the standard window, if you just go to zoom and then go down to standard, it just puts it back onto that standard window. So again, the calculator is a really great tool to check your work, but you need to be able to solve these algebraically. Don't just do these on your calculator. That's not what we're trying to learn. All right, let's go to finish up this last question. And so this one is taking us back to one of the application problems that we did before with compound interest, and it's asking us to use this formula to find out how long it will take $1,500 to triple in value if it's invested at 12% interest compounded continuously. So this is our formula for compound interest. And we starting with 1,500, we want to see when it will triple. So when it's going to triple, it's going to be 4,500. And so we're trying to see when will we have $4,500. So I'm going to put that in for the A. That's the amount that I have now, or the amount that I'm going to get. My P is my principal. That's what I start with, which is 1,500. And then E, my rate is 12%. I want to write that as a decimal. So I'm going to write 0.12. And then my time, that's what I'm trying to figure out. It's asking me how long. It's trying to figure out how long it's going to take. So here's my equation. Now I want to solve it. So when we were doing these problems before, we weren't able to solve a problem like this yet, but now using what we've learned today, you can figure this out. So again, you want to start by getting this exponential part by itself. So I'm going to divide both sides by 1,500. And that's going to give me a 3. And then I'm going to rewrite it as a log. So I'm going to take the natural log of 3 is equal to 0.12t. And then I can just divide by 0.12. And so my time is going to be the natural log of 3 divided by 0.12. I could put that into my calculator. And you're going to get about 9.16 years. Any questions?